Good morning all. So in today's class we will begin the second module. So in second module we will be mainly looking at, so first of all we will be looking at mean value theorem, and then a special case of mean value theorem which is called the Rolle's theorem. So we will begin with Rolle's theorem and few of its problems, and then we will look at mean value theorem and associated problems. And secondly, in the module we will be looking at what are called indeterminate forms. So that is finding limits where your function is in the indeterminate form. And we will look at a rule called L'Hospital's rule for finding limits in indeterminate form. And thirdly, we will look at what are called hyperbolic functions, then a few results on hyperbolic functions, then how to find the integrals and derivatives of hyperbolic functions. So those are the main things we will be seeing in the second module. So this is comparatively the shortest module out of all the 4 modules. So we will go quickly through this module. So in today's class we will introduce Rolle's theorem and we will see a few problems associated with the Rolle's theorem. So okay, so let us move on to Rolle's theorem and its proof. So by Rolle's theorem, so geometrically Rolle's theorem states that if you are having a differentiable function and if it intersects the x-axis at 2 places, appo namukku differentiable aayittulla function undu. So a differentiable function x-axis ne 2 point il intersect cheyyunnundu. So if that happens, so if your function which is differentiable is intersecting x-axis at 2 points, then there will be always a point such that at that point there will be a horizontal tangent line. Okay, so namukku ee graph nokkinal function differentiable aanu, you can see that at this point there will be a horizontal tangent line. So that is the geometrical meaning of mean value theorem. Ini exactly 1 aanavilla. Okay, this is a smooth curve. Okay, so ivide at between these 2 points the function intersects the x-axis. So here you can have more than 1 point where you have a horizontal tangent line. Okay, and similarly if you have a graph like this, so here it is intersecting at 2 points, so here you have horizontal tangent line at these 3 points. So that is the geometrical meaning of the Rolle's theorem. So we will state that theorem and then we will see how to prove the result. So let us first look at the geometrical meaning. So Rolle's theorem is a special case of mean value theorem. So we will be seeing mean value theorem in the next class. So today we will see just the Rolle's theorem and its associated proof. So Rolle's theorem is a special case of mean value theorem, and it is in the name of the famous mathematician so he is called as Michael Rolle. So theorem is named after him, and let us see the geometric meaning of the theorem. So the theorem states geometrically that if a graph of a differentiable function intersects the x-axis at two places, say A and B, then somewhere between A and B there must be at least one place where the tangent line is horizontal. Now when the tangent line is horizontal, that means your tangent line is parallel to the x-axis. So in that case, the slope will be equal to 0. Our function differentiable aanu, tangent line is horizontal, so slope is equal to 0 means your function has a 0 derivative at that point. So when you write theoretically, that's how we state the Rolle's theorem. So if f is a function which is differentiable on continuous and closed interval AB, and if it is differentiable in open interval AB, and if at the end points A and B, if your function is equal to 0, then there is at least a point such that the tangent line is horizontal, so that means there is at least a point C belongs to the open interval AB such that f dash of C is equal to 0. So let us state the theorem. So this is the proper theorem. So that's the Rolle's theorem. So let f be continuous on the closed interval AB and differentiable in on the open interval AB and if f of A equal to 0 and f of B equal to 0, then there is at least one point C in the interval open interval AB such that f dash of C is equal to 0. So that is the statement of the Rolle's theorem. So if f is a function which is continuous on closed interval AB and differentiable on the open interval AB, and if f of A equal to 0 and f of B equal to 0, then there is at least one point C in the interval AB such that f dash of C is equal to 0. So this is the Rolle's theorem. So let us look at the proof of the Rolle's theorem. So let us see the proof. Now for the proof we have three cases. So the first case is when f of x is equal to 0 for all x in the interval AB, and the second case is where f of x is greater than 0 for some point in AB, and the third case is when f of x is less than 0 at some point in open interval AB. So, we will see the 3 cases and we will see how does the proof work in each case. So, we will divide the proof into 3 cases. So, case 1 is when f of x is equal to 0 for all x in open interval AB, and case 2 is when f of x is greater than 0 at some point in open interval AB, and case 3 is when f of x is less than 0 at some point in open interval AB. So, let us see case 1. Now, in case 1, so if f of x is equal to 0 for all x in AB, f of x equal to 0 ആണ് for all x in the interval, open interval AB, അതുപോലെ f of a and f of b are 0, that is already given. You have defined your function such that f of a equal to f of b equal to 0, and again you have f of x equal to 0 for all x in the interval AB. Then in that case function differentiable ആയതുകൊണ്ട് then f dash of c is equal to 0 at every point c in the interval AB, because your function is actually 0, because f is a constant function on that interval. So, therefore proof holds in case 1. And now let us see case 2. Now, case 2, so assume that f of x is greater than 0 for some point in open interval AB. And now, since f is continuous in closed interval AB, so the given function is continuous in a finite closed interval AB. So, therefore, by extreme value theorem, the function will attain an absolute maximum and absolute minimum in the closed interval AB. നമ്മൾ previous module കണ്ടതാണ്. So, since f is continuous in closed interval AB, by extreme value theorem, the function has, so let us say it has an absolute maximum minimum down. Let us take the case where it has an absolute maximum. So, has an absolute maximum on closed interval A, B. Now, absolute maximum ആണെങ്കിൽ, now at the endpoints A and B, f of A and f of B is 0, and for some point in AB, f of x is greater than 0. അപ്പോൾ absolute maximum ഉണ്ടെങ്കിൽ absolute maximum greater than 0 ആയിരിക്കും. അപ്പോൾ absolute maximum end points ആയിരിക്കില്ല occur ചെയ്യുന്നത്. ഇനി end points അല്ലെങ്കിൽ നമ്മൾ extreme value theoremത്തിന്റെ കൂടെ മറ്റൊരു theorem കൂടെ കണ്ടിട്ടുണ്ട്. end points അല്ലെങ്കിൽ absolute maximum minimum occur ചെയ്യുന്നത് critical points ആയിരിക്കും. So, that will complete our proof.